Good morning, everyone. Today we'll look at the new subtopic of backtracking. Am I audible? Can anyone confirm? Okay, so let's start. So I just said we'll look at a topic called branch and bound, which is basically a you can say extension or subtopic of backtracking. And this branch and bound is generally used for optimization problem, something like minimum cost or maximum profit or something of that kind. So if you look at what happens in typical backtracking, if you do a backtracking, we start with a root node, then go to the next child, and we keep going, then come back, and then go back, come back. So we basically do depth first search. And the optimal solution may not lie here, it may lie here. So our effort exploring this much may even go as a waste. The branch and bound is you look at when you start with, look at different number of childs, so child 1, child 2, and evaluate which of these 4 childs or k childs could give a better solution. Explore only that, and let's say we know currently this child seems to be most promising, then explore this child, look at its subchildren, and now look at this children, this node, this node. These are what we call active node, and see which one of these is going to give me most promising one. So rather than exploring depth first search and going back depth first search, we basically look at which is the most promising one. So we start with the breadth first, but we keep looking at which one gives most optimal and proceed. So it's neither a depth first nor a breadth first, but to look at most promising one, and that's the node we explore. And we look at and then we work out a mechanism, how do we proceed. And that essentially what is the branch and bound problem. And the cases we look at a job assignment problem. Main thing we wanted to do in job assignment was find the minimum cost. Traveling salesman problem, find the minimum cost tour. Knapsack problem, find the maximum profit subject to weight. So this is the first two are minimization problem. The knapsack is maximization problem. And actually between the minimization and maximization, there is not much a basic difference. If you turn the profit to be negative, then your maximization of profit basically becomes minimization of profit because it's become negative, and then you get the answer. So you can turn maximization to minimization or vice versa and work the same way. So we'll look at these problems, and today we look at job assignment problem and travel problem, and tomorrow next lecture we'll look at knapsack problem and something. So far what we studied, first we said to find the best solution we need to do what is called exhaustive search, what is called brute force, or explore all possible solutions and find which one would work. And that means the solution could be n raised to k raised to power n, factorial n raised to power n, or whatever, something of that kind, or even could be 2 raised to power n. They're all exponential. Are we looking at which one could be better? So one is explore all possible one. Then we looked at the other one, but we look at the exponential solution would only work for smaller instances because the moment n becomes larger, let's say n becomes 10, then n raised to power n becomes 10 billion, which is too big a solution space to work out. So the exponential will work for small cases, but real life are much larger cases. So that means for practical purposes, the brute force mechanism is not feasible. In theory, it can work, but in practice, it's not going to give any solution. Then we looked at another approach called dynamic programming. We start building sub-solutions, divide a problem into subparts, solve those, memorize those answers, and make use of those to build the other problem. Then we move to backtracking. Start from a solution space, build a state space tree, and keep building a state space tree, and then see which of the node path from root to the leaf gives me solution, explore all those, and we looked at the space called n-queen problems. We also look at knapsack problem, we look at traditional problem to doing backtracking. And still we see that time still takes exponential time, even though from factorial n we might go to k raised to power n or even 2 raised to power n, but it still remains factorial n, I mean exponential. And now we'll discuss is what is called branch and bound, which is basically further refinement of my backtracking, and which is primarily for optimization problem like min cost or maximum profit or something of that kind. So essentially what we want, in addition to what we do in backtracking, we need to do some extra work. And the extra work is we do place a bound on the solution. Identify what is the best solution. And let's say I'm starting from my, let's say my root node, I explored here, and let's say going this path, I know my solution cost is, I'm doing minimum cost is 42. I'm just taking a number. Now if I explore this path and I determine that following this, my minimum cost is going to be 43, then I know there is no point in going this path because I'll never get more than less than 43, and I already got 42, so I stop right there. I don't even explore further. And that is the key concept of what we call is branch and bound. So basically, place a bound on the best value, whatever objective function is, minimization or cost or maximization profit, and look at current solution to the best solution to the current space and see how does it work. So primarily look at the current bound value, that following this path, what is that answer I'm going to get, compare with the best solution. If for minimization, if the best value with a new current bound is more than the best value, discard it. For maximization, if the current node's value is less than the best value so far, we discard it and continue. And we explain this with an example and continue this way. So when we explore, so I'm starting from root nodes, I explore when do I stop. And let's say by following this path, my best value is 42. And if I'm following this path, I get, say, best value bound going to be 43. And I'm looking at minimum cost. That means I already got a cost which is minimum 43, but my best is 42. So I can terminate right here. So one way is the moment I reach a higher value, I terminate. Or I basically come to a place where there's no feasible solution. By system constraint, something of that kind, we define that constraint. If constraints are violated, we stop there. Or we come to a leaf node, we know we can't go further, then we stop there. And we come to a leaf node, if the leaf node has a solution, let's say this node has solution 41, then we discard this and say my best value is 41. So three ways we terminate, either for the current node, the solution is worse than the best value, or a current node, we are violating some constraint which is outside the problem, or we reach a leaf node and then we cannot explore further, we terminate, and then if my best values, the node value is better than the best value, I bid the best value. And that's the primary approach we'll follow, and that is what we'll basically discuss. We'll look at with a few examples and explain, then you understand how does this assignment problem works. So essentially, let's look at, there are n jobs to be done, and there are n people, and different people do different assignment, different cost. Requirement is one person can do only one job, and one job can be done by only one person. So one person cannot do two jobs, and one job cannot be done by two people. So requirement is one job or one person, no less, and we know cost of each job by each person. It's something like somebody may be good at mathematics, some may be good at computer science, some may be good at physics, and you have problem of given one is physics, one is mathematics, one is chemistry. So you like to do which one to do so that the time taken is probably minimal. Because if guy is good at chemistry, if you give him mathematics problem, he or she may take a lot more time than solving a chemistry problem. So assuming we know the cost, that for each person and for each job what is the cost. For example, let's say we have four jobs: job 1, job 2, job 3 and job 4. And person 1 we call A, B, C, D. Person A does job 1, cost is 9. Person A does job 2, cost is 2. If it does job 3, cost is 7. And similarly for person 2, for job 1 cost 2, for job 2 cost 4, for job 3. So these costs are known. Similarly for person 3 and person 4. Now you have four jobs, you have four person. For each person, for each job, cost is given in a matrix. Now the assignment problem is find a combination such that we can do with minimal cost. I would like you to give a thought for 2 minutes and see what do you think would be the, looking at the brute force, what is the best solution you can find. So which job you want to assign somebody so that you get into minimum cost. Can you spend 2 minutes, work out? Then person A should be given which job, person B should be given which job, C which job, and D which job. And my constraint is one person does only one job, and one job is done by only one person. So no person can do two jobs, or no job can be done by two person. So given this cost, can you tell me what can be the job assignment so that I can find the minimum cost? Spend 2 minutes and probably give me worker solution, and then we tell you how do we solve this problem using backtracking approach. So everybody work on solution, give me. I'll wait for 2-3 minutes. If anyone has a question in between, you can ask, and we'll continue. So spend 2 minutes, find the minimal cost. For example, I would say if I were to do what is called, I'll do, let's say, person A, I do a job 1, person 2, I do a job 2, person C, I do a job 3, person 4, I do a job 4. So my cost is 9, 4, 1 and 4, which is 13 plus 18. So if I do this assignment, cost is 18, but certainly not the optimal one. So I want you to give me job assignment so that we can find optimal solution. Anybody work out, give me the answer, and then we'll look at it. Now, what is B, A, C, D? You have to give me details. B means what? What is per person A? What is job 1? You are saying B is job 1, C is, okay, so A, B, C, D. Amrat is giving a solution. Person A is job 2, person B is job 1, person C is job 3, and person D is job 4. Look at the cause. This is 2, this is 6, this is 1 and 4. This gives you 13, and this does happens to be what is called my minimal cost. But given that a larger number, thanks Kavita and thanks Aswini, it will work out. Now we explore the approach and see how do we approach and solve this problem. So essentially, we look at, first let's find what could be my minimal cost, and then say can we update. So we can essentially look at each row. That means look at the job with minimal cost for each person. So for job 1, I can say my cost is, for person A, minimal cost is 2, for person B, minimal cost is 3, for person C, minimal cost is 1, and person D, minimal cost is 4. This is the lower bound. This may not be feasible because if both person B and C does job 3, that means job 3 is done by 2 people, which is not allowed. But to compute the minimum, at least the theoretical bound we get, and theoretical bound we get is take the lowest cost for person 1, person 1 take 2 here, for person 2 take 3, for person 4 again minimal, and person 4 this. We know this minimal is 2 plus 3 plus 1 plus 4, which is 10. We know that this is not feasible because in this case job 3 is done by 2 people, which is not allowed, but at least this gives me a theoretical bound which basically means I cannot do this in less than my cost of it. So we need to find what is the next best we can do, and that essentially what we will look at. And with this what we will explore and continue from there. So we find a job cost of 10. I given you that this is not feasible because job 3 is done by 2 people, which is not allowed. So how do we work out this problem using branch and bound? And that is basically what we'll discuss. So essentially what we look at, we start from root, look at all possible children's, and then look at which is my most promising children, explore only those. And this is what we call is exploring node. So nodes which are yet to be explored are called live nodes, which are currently being explored called E node. And once a node is explored, it's done, it gets children and continue. Then again evaluate the most promising node and continue with that process till you reach a leaf node, and that's what will basically do that. And keep optimizing. So it may so happen that I start from here, I explore, and once I explore this, I look at this, I look at this. So among these, which one is best? I explore this next. Then I look at all the children among this, and let's say we find this happen to be next best. We explore this. So each time we explore one node, we look at all the nodes, find which is the promising one, and proceed from there. There's not a depth first, not a breadth first. We keep exploring what the best one is and continue that way. And that is what we'll basically look at. Start at root, and we know that my lower bound is 10. And then look at with lower bound 10, my possibility is person A. I have 4 possibility. It can do job 1, or it can do job 2, or it can do job 3, or it can do job 4. So basically we start from root tree, which LB of 10, and first leaves is 4 children. For person 1, this will correspond to job 1, this corresponds to job 2, this corresponds to job 3, and then evaluate the cost of a lower bound. If I follow this path, what is my lowest bound on this, lowest bound on this, lowest bound on this, and whichever node give me lowest bound, I explore that. And that's the approach we'll basically follow in the branch and bound. So we know lower bound of this, so we start from here and then explore as 5 nodes. So now look, if I take job 1, if person 1 is given job 1, now job 1 is already assigned to person 1, that means this job cannot be assigned to anybody else. So person 2 can do anything with job 2, 3 and 4. Person C can do anything between job 3 and 4, and person 4 can also do between job 3 and 4. So once this person 1 assigned a job 1, so we'll look at what the minimal cost for person 2. Person B minimal cost is 3, person 3 minimal cost is 1, for person 4 minimal cost is 4. So my minimal cost happens to be 9 plus. Now we are still saying this is not feasible because this job is being assigned by two people, it's not possible. But we are looking at this, the lowest bound we can get, and we cannot do better than that. So we are calculating the lower bound. So if person 1 does job 1, my lower bound would be 70. If person 2 does job 2, if person 2 does job 2, now what is my lower bound? When person 2 does job 2, person 3 can do from job 1, job 3 and job 4, and minimum cost happens to be 3, so you get 3. Person 3 can do job 1, job 3 and job 4, minimum is 1, we take 1, and person 4 can do job 1, job 3 and job 4, 4, so my minimal cost is 10. So with person 1 that's doing job 2, my minimal cost is 10. Same way we evaluate if person 1 does job 3. When person 1 job 3, now job 3 has already been assigned. That means this job cannot be assigned to anybody else. So choices for person 1 is either job 1, job 2 and job 4. Minimum happens to be 4 because job 3 is already assigned. So this job 3 cannot be done. So minimum for person 2 with 4. Minimum for person C with 5, 8 and 8, which is 5. And minimum for person 4 is 7, 6 and 4, which is 4. So we get 20. And same way we evaluate when person 1 does job 4. When person 2 does job 4, it is 8. So minimum among these three is 3. Minimum for this is 1. Minimum among this is 6. So you get 8 plus 3 plus 1 plus 6, which is 18. So we look at if person 1 does job 1, my lower bound is 17. With job 2, lower bound is 10. With job 3, lower bound is 20. So the most promising one means we follow with job 2. And that's how we build a tree. And I show you the tree construction there. So start with this. So start with root node. We know that this is the lowest bound. And no job is assigned. Now assign job 1 to person 1. And we know when I assign person 1 to job 1, my lowest cost happened to be 17. It's already worked out because 9 is done. Minimum is 3, 1 and 4. We know that this is not possible, but somewhere we'll look at, but this might give me a lower bound. Similarly, person 1 does job 2. Person 1 does job 2. My lowest cost is 10, which is what you evaluated. If person 1 does job 3, my lowest cost is, if person 1 does job this, my lowest cost would be, if you look at it has done job 3, lowest cost is this minimum, and this minimum. So 7 plus 4 plus 5 plus 4, which is 20. And person 1 does job 4, the minimum happens to be 3, 1 and 6. So you get 8 plus 3 plus 1 plus 6, which is 18. This is what we get. Now you look at among these, now so far my lowest bound was 10. I have got 4 possible paths. My lowest bound is still 10 among the 4. So I'll keep this node 1, node 3 and node 4 pending and explore. So I'll keep these node exploring those pending. Since the most promising one is node 2, I'll explore that. Now when I explore node 2 further, look what happens. Now this job is already allocated here. So that means my choices are person 2 can do either job 1 or job 3 or job 4. So I'll have 3 edges from here, which is for person 1 doing a job 1. When person 2 does a job 1, person 1 has done job 2, person 2 has done a job 1, so person 3 can do this minimum and person can do this minimum, and this gives me 30. If person 2 can do job 3, because person 2 cannot do job 2, job 2 has already been assigned here. Job 2 is already assigned, So person 2 cannot do job 3. Person 2 can only do job 3 here. If person 2 does job 3, so this is person 1. Person 2 does job 3 here. That means now person C can do either 1 or 4. Either 1 or 4. So minimum happens to be 5, and they will do 5. If person 3 does job 5, minimum is still 4. These are exploration. We don't know which one. We're trying to find the lowest bound. We maintain the lower bound. And so here, if person 1 does job 2, and we say person 2 does job 3, my lower bound is, this is minimum. I cannot do this because this job is already assigned. So minimum between 5 and 8, which is 5, and minimum between 7 and 4, which is 4, this is 14. Same way we explore person 2 doing job 4. Person 2 doing job 4. So if person 2 does job 4, person 1 job is fixed 2. Person 2 does job 4, which is 7. Now minimum has to be for person C between this, and person 4 this and this. So this minimum is 1. This minimum is, look, this is assigned. Person 2 doing a job 2 assigned, and person 1 job 2 and person 2 job 4. That means now person C can do either job 1 or 3, and person 4 can only do job 1 or 3. Minimum here between job 1 and 3 is 1. That's what you get 1. And minimum between job 1 and 3 person 4 is 7. We do 7, so 17. And this is what we get. So now my number of nodes, if you look at what I need to explore, node 1 has a value of 17. Node 3 has a value of 20. This is a value of 18. This is a value of 13, 14, and 17. So my minimum is this path. And we explore here. So that means we already said this is the minimum. So person 1 doing a job 1, 2. Person 2 doing a job 1. Now that means person 3 can either do job 1 or job 3. We'll explore either it can do job 1. Person 3 can do either job 3 or job 4. So we'll explore 2 trees for job 3 and job 4. So let's explore that. When we explore with job 3, if person 3 is doing the job 3, only choice for person 4 is 4, and this is what you get, and my cost is 30. If person 3 does job 4, which is the next possibility to explore, it does job 4. So this is person 1 cost, person 2, person 3, and my minimum happens to be only this possibility because job 1 is done by person 1, job 2 is done by person 2, job 4 is done by person 3. So only choice for job 3 left, which I need to do on cost is 25. So now look at what I need to explore here. If I look at all my cost, 13, my minimum has to be between this. So where do I need to look at my minimum? So I need to explore my minimum from this 17, yet to be explored, 20, 18, 17, 14, 13, and 25. Minimum happens to be 13. We explore further, and this gives a lower bound of 13. And now see, we already reached the leaf node. That means this is my best value. And you look at all other nodes. When we reach the leaf node, so that means we found one solution whose lower bound is 13. Look at all other possibility solutions. This is give me 25. This gives me 17. This gives me 14. This gives me 20. This gives me 17. So this is my best one, and I stop. I don't have to explore. If anything was lower, I would have explored. And this is what job assignment problem. Any questions about this? Again, you need to work out, and we will look at exercise for you to work out and then do that. So always keep looking at the lower bound. keep updating. Look at the node which is the most promising one. So in our path, most promising one was, first was this, then it was this, then it became this, then it became this. If you were using depth first search, we would have explored this and continued and not something else. So this is not a depth first search. This is not a breadth first search either, but it is the most promising search, and that is what we basically do. We look at now another problem which is called, we already looked at trading salesperson problem and how to identify lower bound and look at. So this is a graph of 5 nodes, cost is given, and job is to find a tour starting from a node and come back to same node. Now what is my lowest tour of the cost? One very simplistic approach is, look, the tour, if there are 5 nodes, there have to be 5 edges. If node 5, tour will contain 5 edges. So what I can do is find the edge with minimum cost, which happens to be 1, multiply by number of edges. This gives me lower bound. But we know that this is not really feasible. This is give me lowest bound, but practically low value, because we need to find a lower which is more realistic. Because this edge is only here, may not be other place. So what could be more realistic lower bound? Because the more realistic lower bound we evaluate, we probably be better off. And sometimes it may not be that easy to identify the approach to take lower bound. It may do few experimentations. So one approach is, now when we do the trading salesperson problem, you look at from each node, we go out and come back. So we may go out this path, come back this path. B, we may go out this path, we come back in this path and go out this path. For C, we may come this path, go this path. So for each node, we are entering and exiting. So my most realistic lower bound would be, look at the minimum cost edge for each node. 2 minimum cost edge, because the cost of that path has to be half average of the 2. It cannot be less than that, because each node has to be entered and exited, but each has counted twice because other node. So that means my lowest bound has to be, theoretical lowest bound is, if I look at 2 lowest cost edge for each node and take the sum of the average of those and sum for each node, that will give me the theoretical lower bound. This again may be feasible, may not be feasible, but at least I got more realistic theoretical lower bound. So how do you find? Look at that. We can probably find 2 nearest node, 2 nearest edges, find the average of 2 and compute. So if you look at this, can you tell me, when you look at the average of these 2 nodes, look at node A. Node A is 1 plus 3. For node B, minimum is 3 and 6. So we did 3 plus 6. For node C, it is 1 and 2. For node D it is 3 and 4. And for node E, it is 2 and 3. And since each has to be counted, we are counting each as twice, divide by 2, and this gives me lower bound, which basically happens to be 14. If you count it out, value would be 14, and that is what you'll basically get. So I got my lowest bound, means my trading salesperson problem, I cannot find a solution less than 14. Even 14 may not be achievable, but I know this is the lowest bound. If I were to take minimum cost as multiplied by 5, which is gives me good lower bound, but it's practically not workable. So try to find more realistic, and that is what we find. And now we start doing a branch and bound and build accordingly. So let's look at how do we explore. Now if you look at trading salesperson problem, let's assume some tour. Let's say my tour happens to be A, B, D, C, E, and A. Remember, when we did that, if I follow this path, I can also follow the reverse. That means my path can be A, E, C, D, B, A. So look at in one case, B comes before C, and other case C comes before B. So we can actually put one constraint, we take any two nodes and say we will follow the constraint B comes before C. Because once you put a constraint, that means we don't have to explore this path, because in this path C comes before B. Because if you can find this path is automatically following towards, we can do that. So while exploring, every time you find C less than B, we can simply avoid exploring it and go further, because we are ready to get solution. So this is the constraint will follow. B should come before C, or we can say E comes before B, or whatever constraint. And then we can follow, and anytime we explore, if the constraint is violated, we simply ignore it. And this is what we do. Now let's consider, and now if assuming how to update my lower bound, consider that we include this as AD. Let this edge is included for whatever reason. If this edge is included, my lowest cost for A would be 5 has to be taken, and next minimum is 1, so it would be 5 plus 1. For B, it is still 3 plus 6. For node C, it is 1 and 2. But for node D, this edge is included, so we cannot avoid it. So look at this as 5, and next minimum is 3, so it would be 5 plus 3. 5 plus 3, and for E, we have 2 plus 3, so my lower bound has become 16. And same way we can keep updating. The moment we include an edge, I'm telling you how to update our lower bound, and that is what is important. That's what you need to make sure. Look at the lower bound, and then we put a constraint. We assume one node comes before C, and we say node B appeared before C. So any path C appears before B, we'll discard that node and we'll continue. And then also understand, if we have visited, let's say the 4 nodes, let's say we visited A, B, C and D, then only choice is E and then E to A. So once we visit n minus 1 nodes, then we don't have a choice. We have to visit n and n to the first node. This is kind of given. We use that to reduce our amount of computation we do, and that is what will basically follow. So let's start building our tree. Start from root node A, and from A we have a choices. I can go to B, I can go to C, I can go to D, and I can go to E. And here we know my lowest cost is 14 here. That's what we looked at. So if I go to B, if from A I go to B, that means this edge is included. If this edge is included, for A, minimum is 3 and 1. So what's my lowest cost? For A, 3 and 1. For B, it is 3 and 6. 3 and 6. For C, my minimum is 1 and 4. Sorry, not 1 and 4. For C, 1 and 2. This is 1 and 2. For D, it is 3 and 4. You get 3 and 4. And for E, it is 2 and 3. So it still remains 14. And this is what we get. Now we look at if I were to follow A to C, what happens? Now look, if I follow A to C, now any path you follow further down, it will be A, C, and somewhere B would come. And now here we are saying C comes before B, and we have put a constraint that will explore only path where B comes before C. That means we don't have to explore this path, and we'll simply not explore it and stop there, because in this path C comes before B, we not explore it. So look at next path, D, A to D. That means we included this edge. When include this edge, my minimum is for A is 5 and 1. That's what you do, 5 and 1. For B is still 3 and 6. For C, it is 1 and 2. For D, 5 is already taken, and next minimum is 3, so it is 5 and 3, and for E it is 2 and 3, so my minimum is 16, and that's the lower bound I basically get. And similarly, we'll explore A to E. Once we go A to E, once I go A to E, I take 8 and my next minimum is 1. So for A it would be 1 plus 8. For B it is again 3 and 6. For C it is 1 and 2. For D it is 3 and 4. But for E, because this is taken, so next minimum is 2, it becomes 2 plus 8, so becomes 19. So if you look at, these are my costs now. Now I have 4 nodes, 3 nodes actually. This is with 14, this is with 16, this is with 19. So this happens to be the minimum, and we'll explore this node and keep these 3 and 4 pending. So we'll not explore this, we'll basically keep 3 and 4 pending and explore node 1. That means now AB is taken, AB is taken, now explore. From B I can go to C, D and E. So if I go to C, B to C, B to C, so now look my cost for what happens. B to C, my cost is A is still 3 and 1, A is still 3 and 1, this is already taken, I can always come back on this part. For B, it is 3 and 6, what we have gone is 3 and 6. For C, and now if you look at C, this is given because I'm coming on this path. So my next minimum is 1. Sorry. What we said is we are going to explore this, and we're going to keep these pending. And once I take next as a C, when I take this, so my path is, if you look at, my path is AB, and we are looking at BC. So for A, my minimum is 3 and 1. 3 and 1. For B, it is 3 and 6. For C, the 6 is already there, so next minimum can only be 1, so we'll do 6 and 1. For D, minimum is still 3 and 4, we'll take 3 and 4, and E is 2 and 3, and this remains 16, so my lower bound when I come to this path has become from 14 to 16. Now explore ABC, we'll explore ABD. Explore ABD means AB and B to D. So now what is minimum cost for A? Minimum cost for A is 3 and 1. That's what would happen. 3 and 1 for A. For B, this is as is included, and this is included, so it's going to be 3 plus 7 and not 3 plus 6, because for B both edges are fixed. For C, I still have choice of 1 and 2. I'll do 1 and 2. For D, if you look at for D, this is given to me now that I'm coming from B to D7, and next minimum is 3, so I will do 7 plus 3, and for E is 2 and 3, and this is what we'll do. So this again give me average of 16, and that is what we get. And next is follow ABE, that means follow path AB and B to E. When you follow this path, again cost is for A 3 and 1, 3 and 1. For B is 3 is incoming and going is 9, so this becomes 3 plus 9. For C, minimum is still 1 and 2, we look at 1 and 2. For D, minimum is still 3 and 4, is still 3 and 4. But for E, because I'm coming on this path, This 9 is a must, and my next choice is 2, which is what I do, and my cost becomes, if I sum it up, becomes 19, and this is what I get. So look at now what are my notes. If you look at, this is 16, this is 16, this is 16, this is 19, this is 19. I can explore any one. I can explore either this or this. These three are minimum, because this I have to keep pending because it is 19. I'm not going to explore further. So let's say we explore A, B, C, and we'll keep, because we want to look at most promising one, and most promising one right now happens to be node 5. We could run node 6 or node 3 either. Doesn't really matter. When I explore node 5, so node 5 meaning my path is A to B, B to C. Now my choices are either I can go to D, I can go to either D, or I can go to E. So I'll have two choices, either to D or to E, and evaluate my lower bound accordingly. So if I do, next is D, A, B, C, D. So look, my path is A to B, B to C. Now if I take C to D, I've already taken all the 4 nodes. That means my only next choices is going to be D to E and E to A. I don't have anything left. So my cost is for A is going to be 3 plus 8. It is 3 plus 8, because once I pick the 4 node, this next is mandatory, and from I had to come back, so I cannot apply minimum. So for A it becomes 3 plus 8. For B it is given to me 3 and C, so 3 plus 6. For C, we know for C it is 6 and 4. This is what we go to 6 and 4. And for D, we come to this and this path. So it's 4 plus 3. And for E, we have come this path and we have to go this path. So it's going to be 3 plus 8. And this gives me a cost of 24. So if I follow this path, my lower bound from 16 becomes 24. Same way, we explore, let's say, A, B, C, E. When I explore A, B, C, E, that means my path is A to B, B to C, C to E. Given this, my next node has to be D, and this has to be there. I don't have a choice. So when I look at cost of A is I'm going on this and I'm coming on this. So cost of A would be 3 plus 5 on the average. So when I look at, for A becomes 3 plus 5. For B, this is 3 and 6. B is 3 and 6. For C, if you look at, I'm following A, B, C. C is 6 and E is 2. So this becomes 6 and 2. And from E, only choice is D. So I go to 3 and 5. So my D has to be this 3, and then next is 5. So, sorry, I'm coming from A, B, C to E, not E. So A, B, C to E. So C to E is 2, 6 plus 2. And E, I have to go to D and this. So this is 2 plus 3 is for E. Sorry, my touch is not working properly, so I end up losing it. So let me come back to the same point. And I get my cost 19 and continue same way. Now I have a look at the cost. I have a 24, 19, 16, 16, 19 and 19. So my lowest cost is this and this. We explore any one. Let's explore this one. When we explore this one, so my path happens to be A, B, D, C. That means A to B, B to D, D to C, C to E, and E to A. This path is fixed. And if you look at the cost, this becomes 24. Or my choices, I can go A, B, D, E, C. Other choices, I can go A to B, B to D, D to E, E to C, and A. This is what we go there. And if you complete this, A, B, D, E, C, A is what we get. My cost is 16. So if we look at here now, I reached the leaf node which is 24. Sorry. This I reached the leaf 24, 19, 24, 16. This yet to be explored. This yet to be explored. This yet to be explored. Already reached the leaf node which is 16, which happens to be minimum. If this is minimum, so if I explore this, there's no point because this minimum is going to give me 19, this minimum 19, so I don't have to explore this anyway. This is 16 minimum, but if I explore, it may become more than 16, not less. Already reached the leaf node 16, so I can stop and got my solution there. And that is what basically will say my best solution is optimal tour is this A, B, C, D, E, A, B, D, E, C, A. So my best optimal tour is A, B, D, E, C, A. And we know that this is node 11 is greater than equal to this, so I don't have to explore this. And similarly, this is 19, I don't have to explore this, and I found my optimal solution. So primarily the objective is look at challenges. How do you find good bound function? It may not be easy, you have to think a lot. Challenge is it's going to be too simple. Like we said, we take a minimum as cost and multiply. It's too simple but doesn't give any benefit. But we don't want to make it too complicated, otherwise our computation becomes too heavy. So to find a compromise, and that is what we need to do, figure out. And there are a number of problems you can deal with, and we do other problems with branch and bound. We'll look at knapsack other problems and see how we can use branch and bound to find a solution. So those who have time, I think you have another class at 10 o'clock. So those who have time, there's the exercise I given you, which was coming from the, I given you the IA 3 of last year. So work it out and you'll find interesting combination. A lot of people made a mistake. So explore this and work it out solution, and we can look at solution in the next class when we deal. If any of your questions, please feel free to ask. And those who have time, they can explore this, work out quickly. Or those who want to drop and go for a next class. Thank you.